Alrighty. Okay. Cool. So I'm going to continue the theme by talking about phylogenetic diversity and biodiversity conservation. So a quick recap. Conservation organisations are faced with the problem of having many species that could benefit from conservation, but having limited resources to allocate to the conservation of these species. So the question arises, how do we allocate these resources to conserving the species? Now, most people would agree that all else being equal, we should aim to maximise the future expected biodiversity. For example, if we have a bunch of grubs and a bunch of butterflies, then we should conserve one grub and one butterfly, not two of either one, if we can only afford to conserve two species. So in this case, it's quite easy to see that this is what we should do. However, in general, the relationship between species is somewhat more complicated. So we need some sort of formal measure of biodiversity. This is where phylogenetic diversity comes in. In this talk, I'll use phylogenetic diversity as being on a rooted tree, being the length of the minimum spanning tree connecting the species of interest. So if we have a butterfly and a grub, then we find the tree connecting those species and sum the edge lengths. This gives us the phylogenetic diversity. So returning to our previous example, if we have two grubs, then the phylogenetic diversity is the sum of the edges on this tree here, which is less than if we have a grub and a butterfly, as we're including more of the long internal edges if we have one grub and one butterfly. So the problem is that in real life, things are a bit more complicated. Different species have different survival probabilities. They cost different amounts to conserve. So how do we incorporate this information? Now, Weitzman introduced the Noah's Ark problem. In the Noah's Ark problem, each species has a probability of surviving if it is not conserved, which can be increased by spending some money on its conservation. And the aim now is to maximize the future expected phylogenetic diversity subject to some sort of budget. So there have been many algorithms proposed for solving particular instances of the Noah's Ark problem and various extensions to this problem. Now, this rich body of mathematical literature contains nice little equations like this here, which unfortunately some conservation managers and biologists have yet to come to fully appreciate. So this creates a bit of a problem because the literature is inaccessible to some conservation managers and biologists who are, after all, the ultimate target audience for this work. To help try and alleviate some of this problem, I recently produced a graphical interface for solving the Noah's Ark problem as part of a Google Summer of Coding project. So in this program, you can load in a tree. You can specify some survival probability relationships, which can be nonlinear as well, thanks to Fabio Parti's algorithm. You can then solve the Noah's Ark problem and examine the solutions. So this allows you to compare different solutions when equally optimal solutions, look at the tree to see which edges are likely to be conserved, and compare the solution to various species-specific indices. The reason for that will become clearer in a second. So the Noah's Ark problem has faced criticism from several sources. Firstly, it has been critiqued for being too simple. We need to include information about food webs or interdependencies among the conservation measures, such as regions, as Charles talked about. On the other hand, it has been criticised for being too complex. So conservation managers that I've talked to say that they don't like to use the Noah's Ark problem because they see it as a bit of a black box. They have to be able to explain to politicians and stakeholders how they prioritise species the way they did, and I feel that they can't really do this with the Noah's Ark problem. At the moment in New Zealand, all the species are being reprioritised for conservation, and the method that they're taking is to rank species according to their contribution to biodiversity, produce another ranking according to their probability of extinction, and produce a ranking according to how much they cost to conserve. Somehow these rankings will then be combined to give an ultimate sort of index of the importance of conserving various species. Now, the Noah's Ark problem, or simply the phylogenetic diversity problem, can't really be used in this instance, as the optimal solutions to the Noah's Ark problem with phylogenetic diversity maximizing problem are not unique. There may be several solutions, and indeed on an ultrametric tree, generally there are a lot of different solutions. So you can't get a sort of ranking of the importance of species, because really you have sort of choices like pick one of these species and one of these species, as opposed to pick them in this order. So this is another problem for conservation managers. So an alternative is that we can use some species-specific indices, which somehow give an indication of the contribution to biodiversity that each species makes. Now these aim to divide the total length of the tree, or part of the total length of the tree, so that's the total PD of the tree, amongst the species in some way. Many of these indices are simple to calculate and explain to people, which is what conservation managers want. So the question is, if we use these indices, if we simplify the problem back down to just using some simple indices, how do we fare? Are we actually doing what we want to do, or are we getting worse solutions than by random, say? So to begin with, I'm going to give you a bit of a flavor for some of these indices. The simplest is the pennant edge measure. This simply takes the pennant edge for each species and allocates it to that species. So it's very straightforward. Another one is the fair proportion measure. In the fair proportion measure, for each edge, you split it equally amongst its descendants. You then do this for each of the edges in the tree. So for each species, you will have a contribution from each edge. For example, this species here will have this entire edge allocated to it, half of this edge here, and 1/3 of this edge here. You then sum these contributions to get the index value. An alternative index is the equal splits index, which is sort of a similar thing, except it splits the edges differently. So Arne Moores and David Redding looked at the world bird taxonomy with the aim of finding out how much these indices, how good these indices are at capturing the phylogenetic diversity contained within the tree. So this figure shows the amount of PD, the proportion of PD that's in the tree that has been captured by a particular set of species as a function of the size of a subset. The lines reflect the method that's been used to obtain that subset. So a top line here is what we get if we pick subsets that have maximal PD. So if we pick the optimal solutions. The line in the middle through here is what happens if we pick subsets randomly. So we just randomly pick a subset of that particular size. The other lines correspond to particular indices. The two ones that I've discussed previously are the equal splits and the pennant edge measure. Now the thing to note here is that they do better than you expect by random choice. So Arne and David are wondering, why do they do better by random choice? And they also noticed that there's a high degree of correlation between a lot of indices. So to this end, I made some progress in answering these questions, of which I'll now give a sort of a brief hand-wavy overview. To begin with, most indices allocate the pennant edges entirely to the corresponding species. So allocate the pennant edge to each species, and then you get some other contribution from the internal edges. Now, very, very roughly, the pennant edges contain about half of the phylogenetic diversity, so the total length of the edges in the tree. So if all of these indices are allocating the pennant edges to the species, then we're allocating about half the PD in the tree the same way amongst all these indices. So this explains the degree of similarity between some of these indices, the amount of correlation that you get. So the question then is, why do these indices outperform random set selection? Now, consider this tree here. If we want to find an optimal set containing 4 species, then because it is ultrametric, we just look back at a point in time when there were 4 ancestral lineages. Each of these lineages defines a clade. There's 4 clades. And the optimal solution for getting a set with the highest PD is simply to pick one species from each of the clades. So pick one species from there, one from there, one from there, and one from there. So why does this then, why does this allow us to get capture more PD than random with the indices? Well, if you consider the pennant edge measure, then the clades of size 1 are obviously going to have the highest value, since they are guaranteed to have longer pennant edges than the other clades. So far, we've captured all the size 1 clades, which if we were randomly selecting species, then these are the least likely clades to actually capture, because we only have one chance with each of them to capture that clade. Now, for the other clades, the key to getting the most PD possible is to ensure that we only select one species from each of these clades. If we select more than one species from a clade, then there will be another clade that has to miss out. So in order to be able to do this, the longest pendant edge in each of these larger clades needs to stand out from the other pendant edge lengths. So if all the clades have one really long pendant edge and the other pendant edges are small, then we will recover the optimal set. So in order to investigate this, I was able to come up with a recursive approach for getting an analytic solution to a distribution of the pendant edges under the Yule model. Now, the solid lines indicate the probability distribution of the probability density function of the longest pendant edge, and the dotted lines indicate the probability density function of the remaining edges. So there's a certain amount of contrast between these probability density functions, which is still, there's good contrast between large trees' longest edges and shorter trees' other edges as well. So there's not too much intermingling there. Now, for different models where this contrast is greater, you will get closer to the optimal solution. If the contrast is less, you will do worse. So this, to a certain extent, explains why we get more PD than we would expect by chance with measures that largely rely on the pendant edges. So this is the problem of using these indices for recovering phylogenetic diversity. But what if we introduce some of the previous aspects that we introduced with the Noah's Ark problem? For example, I considered a situation where unconserved species have some probability of surviving anyway. So if we're just maximizing phylogenetic diversity, we're in essence considering a situation where unconserved species are guaranteed to become extinct. Now, if we allow them to survive, what happens? So this figure is an average over simulated yield trees with 20 leaves where we're wanting to find the optimal set of size 5. So on the x-axis, on the y-axis, we have the proportion of the optimal solution that was attained. So the full problem solved with Noah's Ark approach will always have a value of 1 because it's optimal. And on the x-axis, we have the survival probability of unconserved species. So we want to know what species we should conserve under this situation where unconserved species may survive, conserved species are guaranteed to survive, and all species cost the same to conserve. So what we find is that a random sample quickly decreases as unconserved species are likely to survive. But the other measures actually improve. In particular, the pendant edge measure approaches the optimal solution. The reason for this is that if species are more likely to survive, then the importance of the internal edges decreases more quickly than the importance of the pendant edges, as there are more species below each internal edge. So at least if one of those survives, then that internal edge is conserved anyway. The other interesting thing to note in this figure is that the situation that we previously had, where we're looking at maximizing phylogenetic diversity, corresponds to a situation where we have a 0 survival probability for unconserved species. This is a situation in which the random sample performs the best, and these indices perform the worst. So in more realistic situations, where unconserved species will have some non-zero chance of survival, the random sample is a really bad choice, and these indices actually perform quite well, particularly given the simplicity of an index such as the pendant edge index compared with the full-scale Noah's Ark type approach. So in summary, the Noah's Ark problem is a satisfying approach. However, there's some resistance to actually using it and applying it in real situations. So as distasteful as it might be, if indices are going to be used anyway, then what can we as mathematicians do to help conservation managers? Well, we can inform the choice of indices. As we saw previously on a figure, some indices are better at capturing phylogenetic diversity than other indices. Some actually do worse than expected by random sampling. Now, and while we inform these sort of decisions, we can continue to sort of push out better models forward and try and convince people that they should be using those instead. And there's some interesting mathematical problems that arise out of these sort of issues. So we can enjoy solving those problems until the conservation managers come to their senses and like our more sophisticated approaches. Thank you.
question. I'm thinking of a decision